Thanks so much, Sarah. Okay, let me push continue. Yeah, I'm very excited to be here. I'm really excited to share some of our new work with you guys. This is definitely one of the projects that's sort of interdisciplinary, like Sarah suggested. I'm really interested in figuring out how our large language models work. And at least for this project, we're looking at word order permutations, hence the title, Formatter Word Order Little MLM. You probably were able to unscramble it yourself. But that's going to be kind of the topic for today. So let's see, to pose kind of the main question, we're going to discuss whether our current best NLP models know anything about syntax. I think one of the most compelling arguments that they do actually comes from the generative space. So this is an online demo called Talk to Transformer. Basically, you can put in a prompt and see what the model wants to generate. And if you've played with these at all, they're incredibly fluent. They feel like, you know, almost like a person. They're putting all the words in the right order. So this is an example from the prompts. I love eating ham. I always use this prompt. It's my manager's prompt and it's really cute. Generally makes kind of cute prompts. And so this particular transformer, when given I love eating ham, says, so those of you at home with children will know what a stinky situation it is for them to come home from school. And the first thing they do is pop into the kitchen for their daily ham sandwich. The smell enough is to knock you out. And I have to say, I've never appreciated it more than I did then. I found that if I was able to eat lunch with my son in the lunch hall, I'll be able to do the same with my grandson, but my enjoyment of ham sandwiches ended there as I never ate one again, one particular, and it'll go on from there. I mean, this is incredibly fluent. It's a bit weird. I mean, the context, right? It's like a strained conversation topic, but it sounds very much like an English speaker, puts all of the things in the right order. In particular, like some of the syntactic structure is very complicated. So this particular sentence, I found that if I was able to eat lunch with my son in the lunch hall, I'd be able to do so with my grandson. But my enjoyment of ham sandwiches ended there as I never ate one again. That's got a lot of clauses. It's actually pretty complex. So this suggests to me, at least, that these models have to know something about syntax if they're able to generate such text. What is it? Is a question. Is it anything at all human-like? Are they actually acting like a good cognitive model of a language user, let's say? So models like this are trained on a particular paradigm that you all are probably familiar with, the pre-train fine-tune paradigm, which has basically two steps. The first step is pre-training, the second is fine-tuning. And basically the main thing that we use this paradigm for is instead of training kind of separate models for each task, generation, sentiment analysis, etc., we pre-train one large model with kind of a general purpose objective. Usually this is mass language modeling. And we fine-tune that on the task separately. So basically train it on additional data until it reaches a certain level of performance. And then that is the model that we will use for each individual task. The main kind of exemplar in this space is the BERT model. This is roughly what the architecture looks like. During pre-training, you give it an unlabeled sentence pair, A and B. You give it all of the tokens in that sentence separated by a separator, started by a CLS token. And what you do is you mask out various words in this sentence. And the model is encouraged to predict which words were basically hidden. Once it does reasonably well in that, you can train it to do something like natural language inference, named entity recognition, or QA. For SQUAD, for example, which is extractive QA, you'll basically input a very similar thing, a question-answer pair, and the model will output the span in that kind of concatenated sequence that refers to the answer to the question. So it's a pretty straightforward thing. Now, these kind of models that have been trained in this way have reached impressive performance on many, many tasks. And one of my favorite tasks is natural language inference. And this is an image from the multi-NLI data set that I collected back in 2017. And as you can see, kind of the performance curve on the matched subset of this data set kind of has reached closer and closer to 100 over time. So if you start on the left, that's basically when the data set became public. It was around 70-ish accuracy. As soon as we got kind of the pre-trained fine-tuned paradigm, you see this jump, and it kind of has just like increasing accuracy from then on out. And this is not the only task that has this sort of curve, accuracy curve. In fact, a recent paper came out from Kaplan et al. That suggested the more parameters and the more training you provide a model with, its accuracy is just going to basically increase with no bounds whatsoever. So basically they're saying this is such a useful and fantastic paradigm that we're just going to have kind of unlimited success and improvement. So is this true then? Like, how do they do this? How are they able to, have such high performance? And many folks in the field have said that they're able to do this, at least, for the tests like NLI and SQUAD, which require at least some sort of language understanding, that they're able to do so because they actually know something about the syntactic structure of the sentence. And one particular example from last year showed that you can recover kind of the parse tree for a sentence from looking only at the attention of a BERT model. So basically you can go from this heat map to these trees with not so much noise, which is really pretty compelling evidence. Another paper, a popular one by Tenney et al., concluded that models like this, like BERT, actually recreate the classical NLP pipeline. So they go through all the stages of processing a sentence kind of in the order that you would expect. So they have part of speech tagging, parsing, name identity recognition, etc. Which suggests that if they're kind of learning this in this pre-trained, fine-tuned, end-to-end way, that they probably know something about how all the pieces should go together, and they probably know something, therefore, about syntax and classical, and basically language. But this is just a couple of examples. There are many, many papers that have argued mass language models know syntax on the basis of various different types of evidence. So probes, which are like little classifiers trained to extract information from a trained model, or diagnostic data sets like handcrafted by experts to evaluate some particular skill that the model should have. And on the basis of both of these kinds of evidence, at least there's some suggestion that these models might know something about syntactic structure. But in this talk, I'm going to ask the question, well, do they actually, though? What if instead of actually learning, sophisticated syntactic structure and being able to deal with that, instead they're just distributional models on steroids? They're doing what we would expect, the distributional model to do. They care only about the context of particular words, maybe in a little bit of more complex fashion, but they're not actually caring about the word order and the sentences that they're actually seeing in the time that they're actually seeing them. So before I go much farther, I want to make sure that I'm clear about what I mean by no syntax. I'm interested in linguistics as a cognitive science, and therefore I think of knowing syntax as something that people are very good at. And so I take kind of a human-centric approach to this. So what does it mean for humans to do meaning at all? And how is that related to knowing syntax? There have been, of course, many ideas about this: Aristotle, Wittgenstein, Montague, all the way up through today. And people have worked on this, of course, for hundreds, thousands of years. At least for this project, I'm operating under the standard approach to semantics in the generative linguistic tradition, so the Hyman-Kratzer approach, which says that sentential meanings are propositions. They're represented that way, and they're built up according to structured input. So they're built up from words according to like the order of those words as provided by a syntactic component. Just to give you the actual quote from Hyman-Kratzer themselves, that syntactic representations feed into the semantic representations, and you need that structure to arrive at a meaning. I'm just going to read this one from their classic textbook because I think it's an important one. The inputs to semantic interpretation are the output of transformational derivations. The only requirement for the syntax is that it provides us with phrase structure trees. Phrase structure trees in the standard sense are suitable structures for our semantic rules to apply to them. So in order to get meaning from a sentence, you do need some sort of syntactic structure to be initially provided, but there's not very much restriction on what that possibly might be. It just needs to tell you basically how the words combine. So practically, from our standpoint, let's say we're interested in these models that maybe generate like that first one. This means that if they're knowing syntax in the way a person would know syntax, that the order of words conveys some kind of important information about the meaning. I mean, this is probably an obvious thing to say, but these two sentences clearly have a different meaning. So the person bit the cat versus the cat bit the person. They mean very different things. In one case, the cat is sad because it got bitten. The other case, the cat is happy because it gnawed on somebody. So I mean, completely different situation. It's different. So clearly we want our models to be, sensitive, or at least know something about the order of words. So humans are sensitive to word order, not just because if you swap some of the arguments around, you get different meanings, but there's also some evidence from, experiments in psychology that people are actually able to remember words better when those words are presented in normal sentences than in permuted sentences. So this is called the sentence superiority effect. It's been studied by people like Jonathan Granger and a bunch of other folks at Marseille. But basically what they did is they presented people with little short sentences like "our fox can fly," and they underlined one of the words. They present a bunch of these. And when the time was up, they would select one of the sentences that the person was seeing, and they asked them to fill in the blank. So I didn't read this one, but "she can work now." And the person would be asked, "she can blank now. What is the word that was left out?" And you'd have to say "work." And people are really good at this across different languages. It's something that's very straightforward. We make very few mistakes. Now, the trick is when they present people with scrambled up sentences like "our can fox fly," not "was read that," "can now work she," etc. And then they blank one out. People generally are really bad at remembering this. And of course, it depends on how far back the sentence was and some other factors, but it's much harder for people to remember sentences or words in sentences that were scrambled up than words in normally ordered sentences. And this suggests that people kind of have a preference for normal grammatical, well-ordered sentences. That means, of course, that they're sensitive to word order. So given that, if our mass language models are generally learning syntax in some sort of human-like way via this pre-trained, fine-tuned kind of pipeline, then that means they should know something about word order. And do they? So it's a restatement of the question. Well, first we want to ask kind of like, which tasks should we investigate? So maybe different tasks are different. So I'm gonna, the talk is roughly in one large part and one little part. This is gonna be the larger part. And for the larger part, I'm gonna zoom in a bit on the task of natural language inference. This is a paper that we just submitted the camera ready on yesterday. So please do take a look at it if you're interested. And I chose natural language inference for many reasons, but it's also, it's my favorite task. And so I hope you guys like it as well. So just to make sure that we're all on the same page with natural language inference, it's a pretty classic NLU task, maybe like the prototypical NLU task, also known as recognizing textual entailment. And basically what the person solving the task or the model will have to do is, when given two sentences, the first, the premise, which is James Byron Dean refused to move without blue jeans, and the second, James Dean didn't dance without pants, that's the hypothesis. Given these two sentences, the person will have to determine what's the relation between them. And so there's three possible relations between them. The first is entailment. That means whenever the first sentence is true, the second sentence is true, or alternatively, the two sentences should describe the same event or situation. Contradiction, so the first one, whenever it's true, the second one has to be false, or vice versa. And then neither, which is something else is going on. Maybe you don't have enough information, something about the example is broken, this sort of thing. So given this example, James Byron Dean refused to move without blue jeans, or James Dean didn't dance without pants. What do you think the relation between these sentences is? Is it an entailment, a contradiction, or a neither? Probably some of you have seen this example before. It's a classic from McCartney's thesis. The example is, well, entailment. Yeah, so this is an entailment. So whenever the first one is true, the second one is also true. And how do you come to this conclusion? So to do this task, you have to know that James Byron Dean is the same person as James Dean. You have to know that like middle names in our culture just are, and they can be dropped in some cases. You have to know that blue jeans are a type of pants. You have to know that movement and dancing have a particular relationship, so you can't really dance without moving, right? And then you have to deal with this double negation in the second sentence, that didn't and without have a particular similarity, and together they do something kind of interesting. You have to deal with this difficult verb refuse, and you kind of have to put all these pieces together at once. So you have to figure out what the meaning of the first sentence is, figure out what the meaning of the second sentence is, figure out whether they mean roughly the same thing or can at least be true in the same situations. So it's a pretty tricky task. So why would we be interested in this one? I mean, in general, for natural language understanding, we're interested in it because it kind of requires that you're able to represent almost the full complexity of compositional semantics. You have to be able to figure out how pronouns refer, deal with named entities. You have to deal with lexical entailment, so that a cat is an animal, quantification, modality, all the hard and fun stuff that language provides. You have to be able to reasonably do it in order to tell whether sentences stand in particular relation to each other. But also, given that kind of the beginning, I'd said at least the formal tradition, the generative tradition that works on syntax suggests that you need kind of the syntax to develop the semantics. If the semantics is really complicated, the syntax should be able to help you get to that point where it makes some sense. So if this is kind of the structure of the argument in this portion. So if natural language inference actually requires human-like language understanding, and human-like language understanding requires a knowledge of syntax, and a knowledge of syntax requires at least a sensitivity to word order, then models that perform well on NLI should be sensitive to word order. So it's a pretty straightforward thing. So what are they actually? So if they're sensitive to word order, then we should be able to test this by giving them basically scrambled up sentences, giving them sentences with permuted word order. So generally, when we check the accuracy of a model, we calculate the accuracy over a held out test set, pretty standard. So it'll have some number of examples. Like here I have 1 through 6, and every example for NLI will be a sentence pair. So something like the cat sat on the mat and the cat was fat. This is neutral. The cat could have been fat or not. And we associate each of these examples with a gold label. So this is something that human annotators determined. So just like I did for sentence 1, neutral. And we basically ask the model, can you replicate the gold label for each example? Pretty straightforward. So what are we going to do in the permuted case to figure out whether the model knows syntax. Since we're interested in accuracy on permuted sentences, we're going to permute each sentence. We're actually going to permute it multiple times. We're going to call these examples E hat. And we actually permute it 100 times per example, but you could choose any number you like. And you end up with something like E hat 1. So on sat the mat cat, and cat was the fat. Of course, as sentences get longer, you're going to have more possible permutations. It's going to be harder to reconstruct what the sentence originally meant. And then what we're going to do is, instead of giving the model the original accuracy with the gold label, we're going to get the permuted one and say, does it get the gold label or not? And that's the gold label for the original. So when given the permuted, does it get the gold label for the original or not? And so that's the basic question. So before we go much farther, like, this sounds very straightforward, but how should a human like NLI model that's sensitive to order actually behave? Like, how should it work? What predictions should we have about this? I mean, there's many options, but what's reasonable given how NLI works? What do we think should happen? So one option is that maybe the model just performs NLI. When I described the task at the beginning, I had said that there's 3 labels. One of them is neutral, and neutral is kind of a catch-all, right? If something doesn't work or you don't know what the relation is, you should pick neutral. So if the model's kind of internalized that in a particular way, then it should just give neutral for every single example, because you can't actually tell with an ungrammatical sentence whether it's entailed by another sentence or not, right? Because we don't really know what it means. And so we can't check whether it's true in the same situation. It's like, maybe. So one option is that it should be neutral across the board. This is not what happens. None of the models chose this option. There's another option. Maybe the model's just super uncertain. So maybe it's just like, this is really weird. I don't know what to do. I'm just going to pick something. And then it'll basically just randomly select the label. And this will approximately get you to the most frequent class baseline, which is basically 33% for it to balance through a classification class a task. And so then, we would see basically low accuracy, and it would show confusion perhaps. But we actually don't see this either. There's a couple of other options, but all the ones that we went through in the paper, none of them were what we actually saw. What the model actually does is absolutely the same thing as it did originally. So it behaves more or less like a bag of words model. It sees the words in a weird order, and it pops out the label that it popped out for the original, or that it would pop out for the original. So models often accept permuted examples. That means it assigns to them the original gold label. And so if we have examples like this from the actual data set, this top one is from Stanford NLI dataset, and it says, let's go with the top. So it's an entailment. Boats in daily use lie within feet of fashionable bars and restaurants. And the hypothesis, there are boats close to bars and restaurants. It sees that as absolutely the same as restaurants and use feet of fashionable lie in boats within bars daily. Sorry, it's hard to even read these. Bars, restaurants are there and to close boats. Yeah, so it's really hard. As a human to imagine doing inference in this way, like, whoa, I can't even read them. So it sees those 2 examples as completely the same and assigns to them the same label. And we find that this is actually true, not just for the large pre-trained mass language models, but also for pre-transformer era models as well. Okay, so let's dig a little bit more into how we come to this result. First, we defined a permutation function. It was a really pretty simple one. You could imagine many other ones, but we wanted to start with something straightforward. It was basically a random permutation with the restriction that no word should appear in its original position. This is because we didn't want the positional embeddings to learn anything useful from this. So if it appeared in its original position, let's say word 3, then it might actually, the positional embeddings might help you more in that particular permutation. So we removed that as a possible option. A sentence of length n has n-1 possible permutations. This is generally a huge number. Examples in multi-NLI are really pretty long. We train on both SNLI and multi-NLI, but for longer examples, it's going to be even harder to reorder the words. And we selected from this operation only the unique perturbation. So sometimes kind of accidentally, if you have, let's say, the cat bit the person, you have 2 thes, they might have been swapped. The sentence looks basically the same, but then that's not a unique sentence. So we removed all kind of contentless swaps. And so basically what we did is we trained a model on the normal training set here on the dtrain, the data set for the trained data, and we took the trained model. Then we took the evaluation test set that came with the original data sets, passed it through this permutation function, and got basically a perturbed test set. And that's a list of these kind of scrambled up premise hypothesis pairs. And then we gave it to the trained model and we studied the result. So what happens? So how to read plots. Again, we have this kind of column here, which had all the examples with the gold label and the reaction of the model. But for the second part, we're actually going to split the examples into two parts. So if you say on the Y, yes, so on the X actually is the different, no, on the Y is a different example. So example 1 through 6, and on the X is the number of perturbations of that example. So for this moment, I'm going to go with 6 different perturbations. So every sample was put through the perturbation function 6 times, but in reality, we did 100. Then we're going to split this into examples that were originally correct and examples that were originally incorrect. So for the examples that, if the box was green, then the model got this perturbed example correct. If the box was empty, white, or gray, it did not. Okay. So we looked at a bunch of different metrics, but I'm just going to focus on 2 for this talk here, probability of correctness and probability of incorrectness. So since we split this box into 2 from originally correct, originally incorrect, for the originally correct examples, we were wondering which percentage of perturbations also yielded the gold label. That's going to be P to the C. And that's the number in the whitish part of the box of the perturbed examples that have green. So those are the correct ones. They were originally correct and they were also correct after perturbation. So we have 44% in this example. And that's because there's 18 possible options and 8 green boxes. We can do the same thing with originally incorrect. And so these are actually the flips. So these are examples that the perturbation helped the model. It originally failed, but then if it saw the scrambled example, it got the correct label again. And so for these, we have 10 because for the example number 6, all of the permutations were correct. Example number 5, none of them were correct. Example number 4, 4 of 6. So we got 55% in this example. And this should tell us basically what the model is doing. Is it accepting permuted examples? Are permuted examples helping? Note that for a classic bag of words model, P to the C would be 100% and P to the F would be 0. And that's because if it was originally correct, given the words in the order that it saw, and it's insensitive to word order, it's going to be originally correct no matter how you scramble the words around. If it was originally incorrect and you scramble the words around, it's going to be incorrect still, because if it's a bag of words, it has no interest in word order. It doesn't use that for anything. So that's like a kind of idealized bag of words case. And we're going to ask basically how close to that idealized bag of words case are the models that we actually have. So the transformer models that we all love and use every day. So we trained a couple different models, Roberta, BART, Distilbert on the transformer side. And then we also looked at non-transformer models like InfraCent, ConvNet, and BILSTM. We trained them all in the multi-NLI data set up to basically state-of-the-art levels around 90-ish. Then we fine-tuned, the fine-tuning is up to 90, excuse me. Then we fine-tuned on normal multi-NLI. And then we evaluated on a couple of different data sets. We took the original test set, the multi-NLI test set, permuted it. We took the SNLI test set, which is kind of an in-domain data set. It was collected in a very similar way. Slightly different sentences from they're from captions instead of from a bunch of genres, but it's very similar. Permuted that, want to see basically, is there transfer between similar domains? And then we looked at the adversarial NLI data set, which is out of domain. It's collected with a model in the loop, a model adversary that the annotators are trying to fool. So we were curious about like how different domains of data might affect it, and generalization to both in and out of domain data. So preview of the results, about 90% of the data sets in SNLI and multi-NLI have at least some permutations that get the gold label. So it is accepting permutations. And the effect appears both for in-domain and out-of-domain data as well, for transformers and non-transformers. So just to get a little more zoomed in on the results, we do see that P to the C is much larger than P to the F across the board. So for multi-NLI and SNLI, the in-domain data, P to the C is roughly 70-ish, some for SNLI is a bit higher, 76-ish. And P of F is around high 30s to 40s. So P of F is pretty low, but it's not absolutely minimal or minuscule. And this suggests that 30 to 40% of the original MIST examples actually had some permutations that enabled the model to get the gold label on them. So this is not strictly 100% of bag of words model. That would be 100 and 0, but it's moving in that direction, right? So it is actually like bag of words like, at least more than we might want. So for the examples that flipped, they often looked something like this. So we would see the original, like Castlerig near Keswick is the best example. And a good example would be Keswick near Castlerig. Those are entailments. They're basically paraphrased. And the original Roberta large model got a contradiction. And when we scrambled it up, best Castlerig near example Keswick is the, And Keswick example near good Castlereagh would be a wood. It all of a sudden gets the correct entailment labeling. So there's a bunch of examples like this, and it's not exactly clear what's happening with these. It's not just transformers. We do see that the effect is weaker for the non-transformer models. So they still have a higher P to the C than P to the F. And like the P to the C is actually much higher in some cases, which suggests that these are also similarly bag of wordsy, but the effect is slightly attenuated. These are weaker models. So it's not like it's just a transformer problem. The next question we had looking at this data is, or looking at these results, is like, which permutations does the model want to accept? So is there something about particular perturbations that makes the model want to give them the original label? Our first thought is, of course, if we preserve local word order, if, you know, it's a random permutation, but if we look at them and we look at the ones that preserve local word order, are they more likely to be accepted? And the answer is roughly yes. So we looked at blue 2 and found that percentage of permutations correct increases with more bigram overlap. So on the X here, we see increasing blue score, and on the Y, it's the percent permutations accepted correct by the model. And we can see that the transformer models at the top, I mean, all of them kind of go up at the right edge, suggesting that as more local word order is permuted, so as is preserved, as the permuted example is closer to the original, then the chance of acceptance is going to be higher. That makes some sense. However, this is not quite enough to explain the full effect. So we kept digging around a bit. We wanted to know whether there's something actually a bit more abstract going on in these models. And we were curious about whether the particular neighborhood, if it's a bag of words, whether the particular neighborhood that words appear in the permuted example is somehow more like the training distribution. Like for a flip, if you have a permuted example and an original example, if the words in the permuted example kind of match the distribution of the training data more than the original, then that might explain why there's a flip, right? Because it's actually pulling on some distributional information about the neighbors of the words from the training distribution. So we computed sort of a signature for this neighborhood idea, but we made it a bit more abstract. We looked at the part of speech of the neighbors, not just who they are, but are they nouns and verbs and stuff. So if you look at this example here with Mary had a little lamb, we basically would say if Mary is our word of interest, within a window, how many times is there a verb versus a noun? So we looked at the probability of 17 universal parts of speech tags, and we looked at the probability of those parts of speech tags to lie within a window K, a bidirectional window, and we compared the probabilities with scrambled sentences. So for here in this first example, Mary, if we have a window of 2, we'll have no nouns in it. But if we look at the second scrambled version, Mary will have a noun in it. And so the part of speech signature will change to reflect that. So for each word in the training corpus, we compute its POS signature, take the average. And then for each test example, we compute the POS signature for that particular example and for its permuted one, and try to figure out basically which one is more similar to the original training signature. And then we can calculate basically the ratio between the two, given that they're both related to the training corpus. And this is what we find. We find actually that we call this a mini-tree ratio. A higher mini-tree ratio is on the x-axis towards the right, is greater than 1. So if the permuted sentence had a POS neighborhood that is more similar to the training corpus than the original test example, then we would say the ratio is higher than 1. Otherwise, the original test example was more close to the training distribution. And we can see as the ratio increases, at least for the transformer models, the percentage of permutations is correct. So in a sense, they're acting sort of like a bag of words-ish. They're maybe associating some sort of abstract information with particular words. So they're saying like this word usually has nouns nearby. And that's sort of like syntactic structure, but it's not really interested in the particular word sentence you're looking at now and how the words combine in that particular sentence. It's more or less thinking about like how in general this works for this particular word. And so that suggests, you know, it's not actually sensitive to the particular word order. We also checked it with humans. So we had 2 NLI experts. Actually, one of them is me. I don't know which one. I'm either X or Y. But our co-author, Kostuv, the first author, permuted 200 sentences of varying length and asked us to determine what the original label was. And we did our best on this. And of course, we know that NLI is a roughly balanced through a classification task. I know some things about NLI because I've been collecting data in this space for a while. Things like, entailments have particular words in them sometimes in the SNLI data set. So there's some information we knew above and beyond, kind of like a naive annotator, but still our accuracy is way lower here than, the accuracy of the large transformers. So they're about 90-ish. We're at like 60 or 40 or so. Our D to the C and D to the F, again, these are also pretty low. So one thing that we didn't know when we were doing this is that actually the Roberta model got every single one of these examples correct. So COSTUV select only examples that the Roberta model accepted. And so we, of course, did not reach 100% accuracy of acceptance of the Roberta model for these particular examples. Some concurrent work to ours actually looked at different glue benchmark tests and did something similar with untrained annotators. And for the NLI portion of that work, the MTurk workers that they used could only predict up to 35% accuracy for the scrambled examples. So it's not an easy task at all. People really can't do it in the least. We also did it again with Chinese. We wanted to look at another language. There aren't that many data sets in NLI in different languages, but there's a really large new one on Mandarin Chinese. And we found basically a similar thing. So it's not that there's some sort of particular quirk of English. There's not a tokenization issue or something. It seems like this is a general finding. So again, the Chinese NLI model also had high P of C, low P of F. And it seems like this is obviously an issue. I at least don't want models to kind of succeed where humans don't succeed. That seems a little bit counterintuitive. So what should we do about it? We did one kind of simple first attempt, which was a maximum entropy training. And basically that meant while we were doing the fine tuning step, we would show some scrambled sentences and try to get the model to maximize its entropy on the scrambled sentences. And that's following some work by Tome et al. In the context of machine translation. We just kind of tacked on entropy as an additional loss term. And we found that this was, it worked pretty well, which was kind of nice. It's a simple technique, but it was able to keep high accuracy on the original test set and decrease the percentage of accepted permutations considerably. Now it doesn't decrease them enough, but it's a good start. And we think that there's room to improve here, and it'd be really interesting to see further attempts on this point. Okay. So what were the takeaways of this portion? We found that all of the tested models are largely insensitive to word order permutation, although people are not. We also found that reordering words can sometimes cause models to flip classification labels, so get the example right when it used to get it incorrect. And we've made some kind of tentative first arguments based on this pos neighborhood information thing that at least some distributional information is learned by these models, and that kind of enables them to perform reasonably well above and beyond what we had from non-transformers. So it might be that they're learning something like this, they're memorizing this kind of higher order distributional information. So that was kind of the first step, really zoomed in on NLI, but we had a bunch of outstanding questions after having done this project. We were like, well, what about the other tasks? Is this just an NLI thing? Maybe other tasks are less sensitive to permutation. Maybe NLI doesn't actually require as much syntax as we expected, right? That would be disappointing for me, but could be the case. We were also wondering, maybe the original pre-training on the large corpus with the MLM objective, maybe we should consider permuting at that stage as well to see what happens there. It could just be that everything is learned at that step and fine tuning is largely ignored, and that might be the reason for our results. And so we started pre-training large Roberta models on scrambled data. And so that's the second point, or the second part of the talk. And these are my collaborators, COSTUV, Duca, Robin, Joel, and Dawa. COSTUV was the original author on the other paper as well. So in the first part, we only really looked at the effects of evaluating on disordered data. What if we actually just pre-train on it? What's going to happen? One of the benefits of working at a large company is that you can actually have access to this kind of compute. So we went for it. So we wanted to look at a bunch of different models and baselines. For our models, we looked at a Roberta base model with 125 million parameters, 768 hidden size, and 12 layers. We trained on the BookWiki corpus with 100K updates, 8K batch size, etc. We wanted to have a couple of different types of models. We wanted a model that had sort of no syntax and a low distributional prior. And for this, we used a model with no positional embeddings at all. So we just removed the positional embeddings. We also used a model with all of the words selected randomly from a corpus based on either their unigram frequency, which is the unigram frequency example, or uniformly. We also had a random initialization model, so just an untrained version of Roberta. We also wanted to look at an example that had no syntax but had a high distributional prior. And for this, we had, again, random shufflings, but we did this at different gram sizes. So we did it at the word level, 2-word, 3-word, 4-word. Of course, 4-word is closer to the original than the lower gram sizes. And then we took our naturally trained model. So we wanted to see basically how do the other models compare to the naturally trained one. We measured perplexity for all of these guys, and the naturally trained one is on the right. And then the no positional embeddings guy is on the left. And as you would expect, the no positional embeddings guy has the highest perplexity, followed by the unigram. Which tasks were we curious about? We wanted to get a big sample. So we took a subset of the GLUE benchmark. We did QQP, QNLI, MRPC, et cetera. These follow a range of natural language understanding tests, semantic equivalence, paraphrasing, et cetera. And then we also looked at PAWS, which is a particular paraphrasing data set that's kind of created to look at sort of word disorder, like the kind we're interested in. So it was really a kind of a cool data set. We want to see what would happen here. And here's kind of the initial results. It's a very colorful table, but we split the models into low distributional prior on the left and high distributional prior on the right. And on the x-axis, we have the unigram random, uniform random, no positional embeddings, and then the random initialized model. And then we have the n-gram sizes going from 1 grams to the natural. And as you can see, the natural, of course, on the right end has the highest performance, as you would expect. But the random scramblings, none of them really degrade the performance very much, except for COLA, which is a grammaticality judgment data set. It's a bit noisy, but it does degrade somewhat, perhaps, as the n-gram scramble. For some of the data sets, there's very little difference on either side of the dotted line, right? So if you look at QQP, it's at mid 80s with the low distributional prior as well, with the unigram random sample. Even the no positional embedding model does pretty well in QQP and SSE2. So it seems like tasks do vary somewhat, but in general, there's not as much of a change as you would expect between the two halves of this graph. So what exactly is it that we observe? There's a couple possible explanations for this kind of a finding. We can either say that some of these tasks don't need word order information to solve them, or we can say, or maybe word order information can be learned in some way from fine tuning. Which of these is true? Are both of these true? What's going on? So we wanted to look particularly at the fine tuning step. So not only did we train on either ordered or disordered data, but we also fine tuned on either ordered or disordered data. So we had basically a 2x2 design: normal training, normal fine tuning, normal training, permuted fine tuning, permuted training, permuted fine tuning, and permuted training, normal fine tuning. And we're going to look at kind of the difference between these in a sec. So here are the main tasks. The blue is the natural word order fine tuning. The orange is the random word order fine tuning. And then on the x-axis, we have the models that have been trained on different gram sizes or from the random sample, the unigram random sample. And so we can see that the distance between these two bars is actually not as big as you might expect, though it does vary across tasks. So at least for some of these tasks like QQP and QNLI, just like we saw in the past, in the other plot where basically there was no difference between the two halves, there's very little difference here as well on fine tuning. So if you fine tuned on natural word order for QNLI or QQP, you don't actually get that much benefit. The blue bars and the orange bars are super close together. For 3 of the tasks, MNLI, SSE2, and MRPC, you do see some more distance there. So fine tuning on normal word order will get you something on the test set, right? A little bit more benefit from actually seeing correctly ordered examples, but it's still just a little. And then for the last 3, word order seems to be able to be taught during the fine tuning stage. So you see much more of a difference between the normal and the random word order. So the distance is much higher. So this suggests that sometimes you can learn some reasonable word order through the fine tuning step. Okay, so, something weird happened to my slides. We also want to look at probing, since probing is one of the best ways to argue that a model knows something about syntax. So we looked at 2 different kinds of probing. Non-parametric probing, which is done with diagnostic evaluation data sets, and parametric probing, which is done with basically training a small classifier on top. For the non-parametric probing results, we looked at, I mean, this is just one data set, we had a bunch of them, but this is the Linzen et al. Stimuli on subject-verb agreement. We see that once you start scrambling up the words, you do see significant differences in how well models pass this evaluation data set. So the original does pretty well. The conditions have different distractor terms between the subject and verb, or different distractor terms in general. So there's some differences here, but the performance of the original model is pretty high. It's above 90. But as you scramble up the word order, the results go down. So it does seem like the original model does know more than the scrambled ones, at least according to this. And for the parametric probing results, it's a bit more mixed. Is not very much impact of the word or the word scrambling on the parametric results. So for three of the different kind of tests in Centival probing, we see that the original model does the best, but in others, different random scrambles does the best. And we basically think that the probing is not really resolving this very well. So what are the main takeaways from this? It seems like MLMs do not actually need to rely on the classical NLP pipeline to achieve high task accuracy, because completely reordered words is not part of the pipeline, and needing syntactic information is part of the pipeline. So it seems like it's just not what's happening. Instead, distributional information gets you a lot farther than you previously thought. I think we need to be a bit more careful making claims about MLM models knowing syntax. We should probably be a bit more explicit about what we mean by knowing syntax in these cases. And it seems like these large transformer language models don't appear to have kind of inborn a strong inductive bias towards learning a human-like grammar right out the gate. In other words, you can't just get UG for free. If you want some sort of universal grammar, you're going to have to put it in yourself. There's many different things to do coming up soon. We're still working on things at this moment. So if you have questions or ideas, we'd love to hear them. Some things we've been considering is, what about other languages? We've looked at English and Mandarin, but both of those are pretty word order and flexible. I mean, Mandarin's a bit more flexible than English, but what about languages that actually do scrambling kind of natively? So German and Japanese, what happens with those languages under permutation? Are the models kind of reacting differently to it? We talked about different ways to mitigate the issue of accepting things you shouldn't accept. Max-end worked pretty well, but there might be other possible options. The questions also suggest, like, do we think that these NLU tests, like question answering, NLI, should enable models to learn something human-like, but it seems, at least in this case, they're sort of failing and ending up sort of like a bag of words thing. So do we need better tasks that can encourage models to learn more kind of syntactically sophisticated things about language? Do we need better models that have maybe different inductive biases, or maybe both? I mean, probably the answer is yes to all of those questions. Is there another way to mitigate this effect, perhaps with language grounding? Maybe if you have some outside world that you're thinking about, the word order will all of a sudden become more important. It's possible. Can we actually split this kind of unnatural language understanding setup into two? So maybe first step would be depermute, and the second step is do the task, and then we can figure out like where the failure is a bit more. This is a really interesting possible option. We were thinking about this as well. Are there other tasks we didn't consider that might be affected? What about natural language generation? I mean, there's tons more questions. At least for this latter one, we've started going in that direction a bit. So we've been looking at permutation in NMT. This kind of actually is supposed to answer both the top question, what about other languages, and the bottom question, what about generation, because you get both at once. We were kind of looking at, with this project, how robust models are to permutation and translation. So if you scramble up the models, will they pop out scrambled data, or will they pop out correct data? And put another way, if you give it scrambled data, will it hallucinate the correct translation regardless? What happens here? We do find that all of the models are a bit more towards being on the robust side. So they're basically going to be more likely to hallucinate out a correct translation than to spit out something with the scrambled word order. The interesting thing about this project you can take a look at now, it's also an archive, is that we look at very particular perturbations. So not random perturbations, but we actually use parse trees to perturb in a very particular way. So there's many different ways to go, but it does seem like our models are maybe a bit more bag of wordsy than we would like, or at least they're not looking closely at the syntactic structure of the particular sentence at hand. So I think our final thought for now is it's not quite enough. the model should succeed where humans should succeed. If we want a really good model, it probably should fail where people fail as well. Okay, great. Thanks so much, everybody. Look forward to your questions.
Thank you very much, Adina, for this